All right, folks, welcome back. Another course of chemistry. And this lecture is called Classification of Matter. Okay, so I will say a few words about science in general. Okay, so chemistry is one of the natural sciences. It has a long history. And I just spent, I would say, about 10 minutes kind of like motivating why it is what we're doing and why do we do it in a particular way. This also holds for physics and for geosciences, whatever kind of natural sciences we're dealing with. It's the same kind of method, same kind of history. So I like this picture a lot. I think it's beautiful. And you may have gotten those moments. I think we all have. You look up in the sky or anything else around you and you wonder, how can all of this be? Why is it so beautiful and amazing? Now, one way to address that and to try to kind of like get a grip on all these beauties around us is to kind of, give it a scientific description, try to put some elements in place. And that is more easily said than done. And it's always fun to realize, put yourself in a situation thousands of years ago. So you're one of those Greek thinkers, and you lie on your back, you look at the starry night, and you wonder, what is that light there in that far distance? What is that? Right now we know it's a star. And our sun is a star too. We know that. But back in the day, of course, I did not know. How do you actually come to such a conclusion? That is not trivial, right? I mean, right now in our lifetime, we know so much. We take a lot of knowledge for granted. Knowledge that has been accumulated over the years. Right? But this is not trivial stuff. All this knowledge took time to build up. So it's fun to realize that sometimes it's actually not trivial to come to a certain conclusion. So these people lived in those ages where not a lot of things were known. Okay? And they were starting to think about what is matter? I mean, how should we think about matter? Can we give proper descriptions of matter? Right? So this person, Thales, he says everything is made out of water. Okay? So he was trying to understand why certain materials have certain properties. And his way of thinking about it had to do with it contains different amounts of water. Maybe water acts in a particular way in different materials. Okay? Democritus says, well, I don't think that's the case. He says, I think that materials are based on an accumulation of many tiny little particles all together that are in turn indivisible. So at the most fundamental level, I just have a whole array of particles together, and they form the material on a larger scale. Is the atomistic theory that we know now is the best way to think about materials. But in those days, they did not know. So Democritus actually is a person that lived at a later time than Thales. However, Aristotle, you may know him from philosophy classes, was a person that lived at a later time than Democritus, and he did not believe this assertion of Democritus. He said, he said something, but the computer stopped. Okay. I don't know what happened there. Yeah, okay. He says the materials are not made out of indivisible particles, but they are composed of different amounts of fire, earth, water, air, and ether. Okay, so it's a very different way of thinking about materials. Now, I mean, all of these things, I mean, they can be true. I mean, how do you know? I mean, at some level, you can say anything you want. So how are you going to discriminate between these different worldviews, if you want? Okay, so how can we be sure that we know now Democritus is probably the person that gave the best description, but how do we know that? Well, it turns out that if you actually start to do experiments and test things over and over and over again, that you at some point can arrive at conclusions that make more sense than other conclusions. And then at some point you may be able to rule out some hypotheses and confirm others. Okay? So basically, you take materials, you start to look at them very carefully, manipulating them, do experiments on them, a whole series, and based on a logical kind of deduction, you can arrive at certain conclusions. Right? So this is something that people started to do very early on, but really they were ramping up in medieval times and accumulated into kind of a method that we now call the scientific method. Right? So this is kind of like the early days, and in terms of chemistry, those were the alchemists, and they were really fascinated, of course, by turning everything into gold. Everybody wants to be rich. Okay, if you're a poor person, of course, what you want is more money, and one way to get at is to have more gold. If you can turn dust into gold, then you are golden, right? So, but you have to be able to do that, and so in order to do that, motivated by this kind of like, say, pressure for economic welfare, you kind of like start to experiment, so to manipulate, and you actually discover a whole bunch of properties of matter that you had not encountered before. Okay? Now here's a person that was also in that tradition, one of the later ones. Okay? So this is we're almost leaving the medieval times here. And he says, why don't you just like forget about making gold, but instead use the methods that we're working with to do something good. For instance, finding medicines. He was a person who was very motivated by helping other folks, other people, medically. He said the best way I can do that is by actually using these methods, like observing, experimenting, and trying to understand how the human body works, and then try to help the person. This may seem very trivial, but this is not trivial because most medical practices were based on mystic beliefs that had not necessarily anything to do with a logical deduction of observations or the use of observations. Okay, so he actually used observation and logical deduction and did something good. For instance, he says infection comes from outside the body. Okay? Which is something that people did not know. People thought if you get an infection, it comes from you because you did something bad. Right? And now we know it's a little microorganism that attacks you and sits there, it makes problems. Right? Usually observing that, if you take those things out and put people in different situations, you actually have less infection. Okay. He was still like a person of his time. For instance, he still believed in bloodletting, cleansing through bloodletting. Not something that was proven, but this because the belief was so strong, he still thought it was a good practice. Okay, so what leaves us here, basically we have this method of trying to get closer to, I wouldn't say the truth necessarily, but to a better description of what matter is. Okay? And so I want to make a distinction here that method is very different from an opinion. Okay? Scientific inquisition is not coming up with better opinions. Okay? So for instance, if this person says, that's how it is, he may say, it's not. And he'll say, yes it is. He'll say, yes. Okay? So these people have different opinions. Okay? They will never agree on anything. Right? But it's very hard to make sense of those. Okay? So opinions are great for a whole bunch of purposes. They're driving forces in our society, do a lot of good. But when it comes to finding proper descriptions of nature, this is not a good way to go about it. Okay? Scientific inquisition is very different. And this is kind of like a very short explanation of how the method works. You have a clear observation of an event. You give a very proper description of that event, which is frank, which is as frank as you can be, not biased by what you want it to be. Okay, this is really the difference between opinion and scientific inquisition. You have to leave everything that you believe out of your system and just let the observation do its work. It's really hard for people, okay? But that's really important. So, a detailed description of the phenomenon by frank observation. Try not to be biased or colored in your observation. Then, you come with an interpretation. For instance, this is Newton. well-known example. Apple falls. He gives a very detailed description of what he saw. Okay? The apple was sitting there, it was letting loose, it fell on the ground very close to him. Very detailed description. And then he says, well, I can explain that if I come up with this formula. Of course, the story is much longer than that. But he has a formula then, and then, very important, you take that interpretation, okay, and you test it again. Is this interpretation true under all circumstances? Okay? That means if the apple falls from this tree, is this also true for another apple, from a different tree, or from a different object? For instance, if I throw a glass of milk on the floor, does it also obey this law? And if this law describes the falling of objects throughout, then, only then, you can give this a certain amount of credit, so to speak, in the sense that this is a good description of falling materials. Right? This is not an opinion at all. This is scientific inquisition. Okay, so this, of course, is also the method that we follow in chemistry. Okay, so let's say we have a beaker with chemicals. We do an experiment. Something changes. We provide detailed descriptions of these changes, okay, of these phenomena. Then we come up with an interpretation. For instance, this substance must be a reducing agent. Okay, that is an interpretation. And a hypothesis, you have to test it. Okay, you go back. Change something. You can, for instance, say if this is a reducing agent, if I put a lot of oxidizing agents in there, the reaction must be different. So you do that, and indeed, if it is different, then you actually strengthen your hypothesis. Go back several times till you exhausted all possibilities, and then you can conclude that this must be an actual description of this situation here. Okay? Again, this is not an opinion. You cannot just say, oh, I think this is a reducing agent. It must be so. No, you actually investigate that scientifically. All right, here's a couple of people. So after medieval times, people started to use that method consistently. Robert Boyle was one of these people. And he, through that method, the scientific method, actually uncovered a lot of different kinds of laws that are relevant to chemistry. For instance, the gas law and the differences between compounds and mixtures. Robert Boyle's contribution. Also, the corpuscular theory of matter was reaffirmed. Okay, he brought back his idea from Democritus, long forgotten, because Aristotle had dominated the way people thought about matter. He says, hold on a second, my experiments indicate that if you assume that materials are made out of indivisible particles, I can explain all my observations. Therefore, this must be a better description than a description based on, for instance, earth, fire, air, and ether. Right? So based on that, he could throw out Aristotle's description as not being a good description. No hard feelings, just not a good description. All right, another person, very important to chemistry, Lavoisier. He was the person who discovered the conservation of mass during a chemical reaction. We'll hear about that in this class. He also was disproving the phlogiston theory. What is that? That has to do with, for instance, if you burn something, where does the flame come from? Okay? And so people thought that that was a material that was actually baked in the matter that you burned. So the flames were already in there. That material that causes flames was in the material itself. So people had different levels of wood had a lot of phlogiston in it. And water has none of this. So that, of course, is not a good description, because now we know that if something combusts or is on fire, there's a reaction with oxygen in the air. It's nothing intrinsic in the material. Also, the discovery of hydrogen, oxygen, and various other elements can be traced back to Antoine Lavoisier. Okay, so important contributions to the basics of chemistry, thanks to this method of scientific inquisition. People were starting to discover more and more materials and starting to organize these based on their properties. This person, Dmitri Mendeleev, was smart enough to put them in a kind of a table. He organized them in a table based on their properties, their mass, the way they reacted, Okay? And so this is an early version of the periodic table. It's not the version that we have right now, because this is, again, in very early stages. It's differently organized. There's many more elements. But based on this logical deduction, okay, taking elements that you have and then combining them logically, he could say that scandium, which was unknown at the time, he said, based on my ordering, there was a blank here. He says, there must be a material that has these properties and this mass. And gallium and germanium were also not known at the time. And he says, he predicted, because there were holes in this table. He said, based on the fact that this table looks like the way it is, and there are holes there must be elements with these properties. And he called them, well, after the fact, we call them scandium, gallium, and germanium. So this is extremely powerful. Okay? Applying this set of principles, organizing them, trying to make sense out of it, he could actually predict that certain things existed that had not been discovered yet. And he, of course, was right. Okay? So these are extremely encouraging developments that basically told people that they were on the right track in interpreting what matter is. Okay? Now, this is a quote from Mendeleev. He says, "We could live at present day without a Plato, but a double number of Newtons is required to discover the secrets of nature and to bring life into harmony with the laws of nature." What does that mean? He says, look, Plato is a good guy. Okay? He says beautiful things. Nice philosophy. But what we really need is something like Newton, who applies a scientific method and actually investigates things and comes to conclusions that you cannot arrive at by just sitting on a rock on a hill and thinking for yourself. Right? So this is the way the Greeks used to do it. They used to think. Just that thinking, you can actually create your own reality, or basically give an interpretation of reality. He says, that's fine, but that's not enough. We need scientific inquisition, okay? Hypothesis, test it in real life, and see if it is true. And then go back, and then strengthen your hypothesis. That is really, he says, what will bring life into harmony with the laws of nature. Okay, last example, just to kind of like close the story on this. This is Sherry Rowland, who recently passed away, sadly. He was here in the chemistry department. He won the Nobel Prize for the discovery of basically the depletion of ozone in the ozone layer. He says certain materials, CFKs, will deplete the ozone in our atmosphere, and that is not good. Okay, so he set out actually on a campaign to prevent the release of these CFKs in our atmosphere. Successfully, and thanks to him, the ozone layer is no longer, I would say, the hole in the ozone layer is no longer expanded, but actually shrinking. Okay, so this is a very important development. He was a very good atmospheric chemist, done many, many experiments, very meticulous, very scientifically accurate, so to speak. Okay? Took the scientific process extremely serious. So this is a statement that says, chemicals expelled into the atmosphere have pronounced climate effects, okay? Which is something that he observed through his experiments. And just to contrast that with something else, this person says, the greenhouse effect is utter nonsense. Okay? Now, whether he is right on the level of, on the metaphorical level, you can say, who is right? I don't know. But I can tell you that this is abiding by the scientific method and is trying to do the best you can based on scientific evidence. And this is not necessarily so. Okay? This is much more colored and based on opinion. And again, opinions are good in our society. But opinions do not have necessarily anything to do with scientific inquisition. It's a very different way of truth seeking. Okay, so distinguish these two things. The scientific inquisition method is one of the best methods, in my opinion, we have to get to a better description of the world around us. We cannot just simply base it on our own opinions and our own thinking. Okay, so it's all about matter. Okay, so let's look at this last of, I don't know what it is, pineapple juice, orange juice. It looks particularly delicious today because it's kind of hot. I would classify this as a homogeneous mixture. A homogeneous mixture is a mixture because I know there are multiple things in this glass. Okay? For instance, there is water in there, H2O. There's also sugar, sucrose, in there, another compound. Water is a compound, sucrose is a compound. They're all in this glass. Or citric acid. Citric acid is a component that sits in oranges, and it gives it the slightly acidic flavor. Or vitamin C, another molecule, a compound that sits in this glass. Together, they form a mixture which is homogeneously mixed in the sense that they will not segregate out. So on a molecular level, they form a homogeneous solution. Okay? Nowhere in this glass I have one chunk here that is sugar, one chunk here that is citric acid, and one chunk here that is water. They all come together, they're mixed on a molecular level, and thus this is a homogeneous mixture of compounds. These are compounds. Okay, so these compounds that turn out to be pure substances in and of themselves. So if I just have the water, if I'm able to take the water out here and just have the water, I have a pure substance. Okay, so a compound can be a pure substance when it's just by itself. Pure water, or if I just have sugar, a sugar cube, I have pure sugar, which is a pure substance. There's nothing else in it, just sugar. So these compounds, once isolated, are pure substances. But, as you can see, a water molecule, this compound, has still multiple things in it. It has hydrogen atoms and oxygen atoms. Okay? So I can separate water out, and also sucrose, for instance, into individual elements. In this case, carbon, oxygen, and hydrogen. All these compounds here are made out of these atoms, either carbon, oxygen, or hydrogen. Okay, so these are elements. And then the elements themselves are composed of individual atoms. Okay? And the atoms are composed of electrons, protons, and neutrons. So we have a flow here from mixtures to pure substances, which can be compounds. The compounds can be separated out into elements. Elements are composed of atoms. And atoms are composed of electrons, protons, and neutrons. So let me classify this, or put this into a different scheme, which is a little bit more easy to understand. Okay, so I have matter here. I can separate matter into roughly into mixtures, things that are mixed, and things that are pure substances. So let me first look at the mixtures. I can have heterogeneous mixtures. What is that? Well, let's say if I have in one hand some salt, and in the other hand some sand, and I put it together into a small pile, then I have a mixture. But I know this is not a homogeneous mixture. Because on a molecular level, these two substances are not mixed. Okay? It's a heterogeneous mixture. On the other hand, a glass of lemonade is a homogeneous mixture. Okay? There's no locations in this glass where suddenly you have only water or only sugar. It is mixed on a molecular level. Okay. All these mixtures are made out of pure substances, mixed together. So the pure substance then can be separated into elements. Okay. For instance, sugar contains the element carbon, oxygen, and hydrogen. Okay. So the compound sugar is containing elements. Okay. And the elements themselves can also be a material. For instance, carbon, diamond, is made out of only elements, only carbon atoms. It's an elemental material. Okay, so diamond is a material, a pure substance, which only contains the element carbon. Sugar is a pure substance, but it is a compound because it contains multiple elements. It contains carbon, hydrogen, and oxygen. both are called pure substances. Okay, so pure substances, therefore, can be distinguished into two categories. One is the compounds, which means a material is composed of multiple elements, or elemental materials, a material that only is composed of one type of element. Think of diamond, for instance. Only contains carbon. Okay? So both of them, of course, are composed of atoms. Okay? Elemental materials only contain one type of atom. And compounds contain typically different types of atoms. Now, atoms are composed of a nucleus, okay, in the middle of the atom, and then electrons around it. And then finally, the nucleus is composed of a neutron and a proton. Okay, we'll look at these particles individually a little bit better. Okay, so these are the fundamental particles, the neutron, the proton, and the electron that constitute matter. You can go even deeper. You can talk about quarks. We'll not do that in this class. Okay? Don't talk about quarks. Here in this chemistry class, we stop at this particular level. Neutrons, protons, electrons provide us enough information to explain the different properties of materials. Okay. Now we know the classification of materials. These materials can exist in different states. Okay? We all know that. Think of water. Water can exist as ice, which is a solid, as a liquid water, and as a gas, water steam, or water vapor. Okay? In all cases, the water molecule is the same. It's the same water molecule. It is just organized differently. Here, they're all very close together, organized into a lattice. Here, they're still close, but not organized as well, a little bit more chaotically. And here, they're not close at all. Okay? But realize that the molecules themselves are just water. There's no change. There's no chemical change between a solid, a liquid, and a gas. It's the same material. It's just organized differently. It's in a different phase. Here's another rendering of that. You see in a gas, you see little ping pong balls floating around. Those are molecules, let's say. They're moving around. In the liquid, they do too, but much more closely. Okay? And then finally, in solid, they're very closely packed. They still move around a little bit. They're not fully quiet. They still shake and bounce a little bit, but definitely not as much as they could in liquid, and nowhere close to the gas. But the properties of the individual spheres here don't change. It's just the packing and the closeness relative to the other particles that sets the difference between phases. Okay. Now let's look at a couple of fundamental properties of materials. And I'm sure you're completely familiar with this. Okay? But let's just do this anyway. Mass is an important property of matter. And mass relates to the quantity of the material. The more you have, the more its mass. Usually we indicate mass by this letter M. Volume is another property of materials. Volume, of course, relates to the amount of space occupied by matter. Now, sometimes that relates also to how much you have, right? Because if I have more of this particular metal, then its volume will be larger. Okay? But not always so. For instance, if I take this balloon, which is containing gas inside, and if I put the balloon into a fridge, the temperature will get colder, okay, lower, and then the gas will shrink, and hence the volume of the balloon will shrink too. But the amount of gas, the amount of molecules inside hasn't changed. Okay? So the volume is not necessarily dependent only on the quantity of the material. The mass is. This balloon and that balloon have the same amount of gas molecules inside, yet their volumes are different, just because of temperatures. Okay, now density is another very important property. Density is the ratio between these last two properties, the mass and the volume. Mass over volume, that is the definition of density. Okay, so here's an example. This is an example of a high density material. Lead. This is a chunk of lead. It's quite heavy. It's quite heavy for its volume. Okay, so the mass is high for its volume. That means that density is a large number. Now here is, bless you. Here are a couple of bullets. These are lead bullets. Okay, the mass of these bullets is much less than this big chunk of lead. Is the density also less? No, the density is exactly the same, but the density is independent, completely independent from the quantity. Okay, so the quantity doesn't matter. Any amount of lead has the same density. It is mass over volume. The mass per volume unit is the same no matter how much of the lead you have. Here's an example of a material that has a low density. This is bromine gas in a flask. The molecules are very far apart. That means you don't have a lot of material per volume unit. Okay? So per volume, you don't have a lot. You don't have a lot of mass. That means the density is a low number. This is a low density material. Okay. So we talked about the different phases in which materials can be. We also know that materials can change their phase. Okay? So water can melt, meaning it goes from the solid state to the liquid state. Okay? Let's see. So, if you go from the solid to the liquid phase, we call that melting. You know that. This guy is experiencing that right now. Liquid to the gas phase is called vaporization. Okay? So liquid to the gas phase is called vaporization. Vaporization is the typical word we use for this process. Gas to the liquid phase is called condensation. Okay? You probably have heard of that. Liquid to the solid phase is called freezing. Same what happens with water. When it freezes, it goes from the liquid to the solid phase. And from the solid to the gas phase directly. So let's say a chunk of ice is directly changing into water vapor. That is called sublimation. You see a chunk of frozen CO2. Okay, so this is a big block of CO2. You can keep that at low temperatures, will stay as solid. But if you take that out and put it at room temperature, suddenly the CO2 molecules will quickly go into the gas phase without going through the liquid phase first. Okay, so that's an example of sublimation. This little kind of, let's say, vapor you see on top actually is not CO2. That actually is water that condenses on the surface. That gives you these little water vapor droplets. That's what you can see. The CO2 itself you can't see in the gas phase. Okay, so here's a diagram you'll see in the book as well. The solid changes into liquid. That's of course called melting. The opposite is called freezing. We're very familiar with those words. Liquid to gas is called vaporization. We typically do not call it boiling. Okay? That's a kitchen language. We call it vaporization. The opposite is called condensation. And then, going directly from the solid to the gas, sublimation, and vice versa, from the gas to the solid, deposition. That's the last word, deposition. Okay? So recognize these words and know what they mean. This is a picture in the book, so you can look it up. Okay. Let's look at some changes that take place when one of these phase changes takes place. That's a very ugly sentence. Here's an ice cube. When it melts, it turns into water. Okay? And then when it vaporizes, it turns into steam. But during these processes, the density of the material will change. Okay? The separation between the water molecules will change if they go from the solid phase to the liquid phase, and from the liquid phase to the gas phase. Here they will be extremely far apart, meaning the water now has a very low density. Here it has a pretty high density. And here it has also fairly high density. Water is an interesting material because it turns out that the solid form of water actually has a lower density than the liquid form of water, which is quite unique because most materials have their highest densities in solid form, because that's where they are the closest, and then slightly lower densities in the liquid form, and by far the lowest densities in the gaseous form, the gas phase. Okay, so that makes a lot of sense. To think about how far these things are apart, that means the density goes down. Okay. You can also have phase changes between two forms of solid. Let's look at graphite phases. Graphite is composed solely of carbon. Okay? And if you compress this very high pressures, you can turn it into a diamond. It's a very hard process. Extremely high pressures are required. You can do it. In both cases, the element that makes up this material has not changed. Okay? This is pure carbon, this is pure carbon. The way in which they're organized is slightly different. Okay, so in graphite, the carbon atoms are organized in sheets that are stacked, and in diamond, they're organized in this very nice hexagonal lattice, diamond structured lattice. And in all these cases, all these little balls there, spheres, are carbon atoms. Okay, so this is a solid to solid phase transition. Same ingredients, different properties based on a different packing of the atoms. Okay, another very important phase change is the change from something that is a solid to something that dissolves in water. Okay, so you see an example. We'll look at this example several times. This is an ionic lattice composed of ions, negative ions, positive ions. This is a piece of salt, let's say rock salt, or sodium chloride. For instance, if you put it in water, it will dissolve. That means that the individual ions, this is the chlorine ion, this is the sodium ion, will be encapsulated by water molecules and taken out of the lattice and thus floating away from the solid phase. That process continues till there's no ions left in the lattice. Okay? So that means that the lattice is gone. That means you have no solid anymore. This material is dissolved in water. And the way we write that chemically is the following. Sodium chloride, it has an S. That means it's in the solid phase. I put a grain of this stuff in a cup of water, and then, after a little while, the lattice is gone. All the individual ions are now floating about, okay, in the aqueous phase, in the water phase. And therefore, the individual ions now are written down separately with this as a specifier. Okay? This is aqueous. It means they are dissolved. They're encapsulated by water molecules individually. Okay, so these are phase changes, and they should be discriminated from chemical changes. Okay? And a chemical change, it's not just a difference in arrangement. Okay, so a physical change, a phase change, means that I have particles. The particles stay the same. I'm just going to reorganize them, put them in different places, stack them differently. That is a phase change, or a physical change. The chemical change is different. In a chemical change, you are actually forming new materials. Okay? Here's an example, pretty brutal one, of a chemical reaction. This is the combustion of organic materials. A tree is on fire, and that is basically an organic material, wood turning into CO2 and H2O under the release of heat. Another example, this is basically the deterioration of metallic compounds, corrosion. And here's a lovely lady doing experiments in the lab. Okay? Something you will be doing as well. And all these examples, the materials you are working with are not just reorganized in space, they're actually making new chemical bonds. Okay, so different atoms now are making new bonds, forming new materials. Okay, so we'll talk about that very extensively, but just to give you an idea, some very simple examples will help to clarify the difference. What happens if a silver spoon tarnishes? Is that a physical change or a chemical change? Who says physical? Who says chemical? Yeah, chemical. It is a chemical change because basically it is the reaction of silver, which is the spoon, with sulfur to form a new compound, a new chemical on the surface, which is this silver sulfide. Water freezes to become ice. What is that? That is physical. Okay? The water molecule itself doesn't change. It stays water. It just organizes itself differently and goes from a liquid phase to a solid phase. How about this? Sugar cube dissolves in your coffee. Chemical or physical? Physical. Yes, because the sugar stays sugar. It doesn't change. The molecular structure of sugar is the same. It is just surrounded by water molecules. It doesn't form a lattice. It's rearranged into the solution. And it acquires this AQ sign. And this, Tums, it neutralizes your stomach acid. Is that a chemical reaction or physical? That's a chemical reaction. That's right. This is actually an acid-base reaction. Okay? This OH compound then is reacting with acidic components in your stomach, creating new materials. Okay. All right. Well, I think that's probably enough for today. I'll see you again on Wednesday.